Good day, dear student friends. Myself, Mr. Sayyid Hassan Kazi, Assistant Professor, Mechanical Engineering Department, Tondadare College of Engineering, Gadag. In this video session, let us learn how to solve the problem on this simple bar subjected to an axial load using finite element method. Let us determine the nodal displacements, stresses in each element and the support reactions for the bar given. In this bar we have two boundary conditions. Let us have a look. Here this support, here there is a zero boundary condition, displacement is 0, and at this end the displacement, this end may have maximum 0.12 mm because support is provided at a gap. How to handle these type of non-zero boundary conditions, we will have a look in this solution. Let us proceed to the solution. Let us discretize this bar into two elements. There is locate node number 1 here, node number 2 at the load discontinuity, node number 3 at this end. Here we should not locate the node because in FEM we should discretize only the structure. So we have two elements and three nodes, 1, 2, 3. Let us generate the stiffness matrices for both the elements 1 and 2. Stiffness matrix for element 1, K1 is given by, as we know, for 1D bar the stiffness matrix for element is given by AE by L1 minus 1 minus 1. One order of the matrix will be 2 cross 2 because for the element having two nodes. Substituting the values of area, Young's modulus and the length of the element. Area given is 250 mm square and Young's modulus, that is 210 GPa, that is 210 in 10 raised to 3 megapascal, and length of the element given is 150 as here. Young's modulus, area. After calculation we will get 35 into 10 raised to 4 stiffness matrix for element 1. 10 raised to 4 you keep outside and 35 inside, and write the DOF numbers 1 2 1 2 because element 1 it is consisting of two nodes, initial node 1, final node 2. Now next, stiffness matrix for element 2, AE by L, area as given 250, Young's modulus of the material of the element is same, 210 GPa, 210 10 raised to 3 megapascal, and the length of the element 2, that is 150. We got the same result for stiffness matrix for element 2 since the properties are same for the element 2 also. So we got 35 into 10 raised to 4. Keep the same common outside as in element 1, 10 raised to 4 into 35 minus 35, 35, 35. Now write the DOF numbers for the element 2, 2, 3, 2, 3 as the element 2 having the nodes initial node 2, final node 3. Now proceed to generation of global stiffness matrix. Global stiffness matrix K, it can be found out by assembling both the matrices K1 and K2. Since the entire bar is made up of two elements having three nodes, since there are three unknowns u1, u2, u3, 3 degrees of freedoms, hence the order of the matrix for the global stiffness matrix will be 3 cross 3, hence generate a grid of 3 rows and 3 columns. Now since the numbering we made, that is in series 1 2 3, in series 1 2 3, element 1 that is 1 2 and element 2 2 3. From this we can easily assemble these two matrices. That is what you have to do in this shortcut method. If the numbering is continuous like 1 2 3 as here in this case, how to assemble both the matrices? Just highlight the K1 matrix terms into this box 1 2 1 2. Next transfer these terms of K2 into this box, that is 2 3 2 3. Then one common you will get the value, that is 35, that is 2 2 2 2. In both the matrices it is available. 35 plus 35 you will get 70, and the remaining blank boxes you write 0. This is what the global stiffness matrix we got. Now you write the overall equilibrium equation. Ku is equal to F, that is global stiffness matrix just now we have found, into nodal displacement vector, since there are 3 DOFs, 3 unknowns, U1, U2, U3, and next point load vector, that is F1, F2, F3. F1 is applied load at node 1, since it is not given it is 0. F3 applied load at node 3, there is no load applied. F3 you take it as, write it as 0. Next F2, here I wrote 60 into 10 raised to 3 Newton. The given force at the node 2, at node 2 the load given is 60 kilonewton, and the direction of load is in the same direction of element numbering, hence it should be taken as positive. That's why at node 2 I wrote plus 60 into 10 raised to 3 Newton, otherwise it would be negative. Now using elimination approach, we'll solve these 3 equations from the overall equilibrium equation. Elimination approach says, since the boundary conditions are, we have U1 is equal to 0 and U3, the maximum displacement the node 3 is having 0.12 mm. These are the 2 boundary conditions which are known to us. According to elimination approach, no need to solve for U1 and U3, just to eliminate the rows and columns like this. The first row, first column for U1, third row, third column for U3. Hence remaining only second equation we need to solve for U2 value. How to solve that? Just the second equation you write 10 raised to 4 outside into bracket minus 35 U1. U1 is already 0, then discard it. Next plus 70 into U2, that I wrote here, minus 35 into U3. This minus 35 U3 I wrote here because even though this column is eliminated, but U3, this is the non-zero boundary condition, you should consider this term also. Otherwise it will affect the solution. Minus 35 U3 is equal to, that is 60 into 10 raised to 3. Now we will solve this equation to get the value of U2. That is 10 raised to 4. We will get here 10 raised to 4, 70 U2 minus 35 into U3 is 0.12. That is specified value of displacement given is equal to 16 10 raised to 3, that is 6 into 10 raised to 4. Now next we'll proceed to the next page of the solution to calculate U2 value. Now u2 value here we got, after calculation, 70 u2 is equal to 6 plus 4.2 we got, that is u2 after calculation, u2 we got 0.1457 mm, that is the displacement. The node 2 is having a displacement of 0.1457 mm at the point of application of load. So that we got now the displacement values at the nodes 1, 2 and 3. At the left support, displacement is 0, u1 is 0. At the point of application of load, u2 we got 0.1457 mm. At node 3, that is at right side, there is a the displacement we got, that is it is given already specified 0.12 mm, because support is provided at a gap of 0.12 mm. These three values you got, u1 0, u3 0.12, u2 0.1457 mm. Okay, now let us proceed to computation of stresses in each element. Element 1, stress in element 1 using Hooke's law, Young's modulus into strain in element 1. Young's modulus is 210 in 10 raised to 3 megapascal into strain in element 1. Change in displacement between the two nodes, that is final node minus initial node u2 minus u1 divided by L1. u2 we got here E1 is 210 10 raised to 3, u2 0.1457, u2 0.1457, u1 0, and length of the element is 150. And after calculation we got 203.98 approximately equal to 204, and stress in element 1 is 204 Newton per mm square, that is tensile. Hence the tensile stress of 204 Newton per mm square is induced in the element 1. Now we'll proceed to the stress in element 2. Stress in element 2 is Young's modulus into strain in element 2. Young's modulus is same, 210 10 raised to 3 into bracket. Strain in element 2 is change in displacement between the two nodes 2 and 3. Final node u3 minus u2 divided by L2. u3 already it is given 0.12, u2 calculated we have found 0.1457, L2 150. Therefore stress in element 2 we got minus 35.98, that is approximately equal to minus 36 Newton per mm square. Hence compressive stress of 36 Newton per mm square is induced in element 2. And therefore it is observed that the element 1 is subjected to tensile stress and the element 2 is subjected to compressive stress. Now next proceed to the calculation of support reactions. Using elimination approach, support reaction R is given by R is equal to Ku minus F. Now since both the ends are provided with supports, node 1 is provided with support and node 3 is provided a support at a gap of 0.12 mm, hence calculate the support reactions at nodes 1 and 3, that is R1 and R3. To find R1, refer the equation number 1 from the overall global equilibrium equation, that is this is in the global equilibrium equation. You refer the equation number 1 for R1 and equation number 3 for R3 to calculate R1 and R3 using Ku minus F. Now we will proceed to the solution for support reactions. Now here I have referred the equation number 1 for R1, equation number 1 from the equilibrium equation, 10 raised to 4 into 35 u1 minus 35 u2 plus u3 minus this is F1, that is 0. So that after calculation we will get R1 as minus 50,995 Newton support reaction at node 1, that is approximately equal to 60,000 Newton. Okay. Now next calculate the support reaction at node 3, that is R3. That is, refer equation number 3 of the overall equilibrium equation. 10 raised to 4 common outside. 0 u1 minus 35 u2 plus 35 u3 minus 0, that is minus f3. The f3 is 0. Take 0. Now next, after calculation, we will get R3. We got minus 8995 Newton, approximately equal to 9000 Newton. By adding these two, that is support reactions at two supports, 1 and 3, if you add, we will get approximately, this is minus 51,000 and minus 9,000, approximately we will get minus 60,000 Newton, that is minus 60 kilonewton. Since the applied force on the bar is 60 kilonewton, obviously the support reaction must be 60 kilonewton, hence the answer is verified, it's correct. Okay, thank you student friends. Next video session I will explain you about the penalty approach. Thank you, take care and stay healthy.